In this module, we shall learn about the regression analysis in detail. Let us begin by understanding its meaning. Unlike correlation, which studies the relationship between two variables, regression analysis involves prediction of average value of dependent variable on the basis of fixed value of the independent variable. The simplest form of regression equation is a two-variable linear regression line which is given by y is equal to a plus bx. Here x is the independent variable and y dependent variable. A is the intercept, b is the slope of the line. A regression line tells us the estimated effect on y of a change in x measured by the slope. The slope measures the amount by which y changes corresponding to a unit change in the x variable. For example, P is equal to A minus BQ shows the relationship between price and quantity demanded of a product. Population regression line PRF is generally given by yi is equal to beta O plus beta 1 xj plus ui. The population regression line SRF is estimated using a simple regression function given by y hat I is equal to beta hat 1 plus beta hat 2 xi plus u hat I. Here beta hat 1 is the simple intercept and beta hat 2 is sample slope coefficient and u hat 1 is the residual term and is assumed to be normally distributed with mean 0 and standard deviation sigma. These parameters are the estimates of the population parameters. The concept of statistical inference has two branches, estimation and hypothesis testing. The theory of estimation consists of two methods, point estimation and interval estimation. Let us understand them in detail. After studying this module, you shall be able to know the concept of ordinary least square, understand how to estimate an OLS estimator, know hypothesis testing of regression parameters, understand the problem of prediction. Let us begin by understanding the methods of estimation. There are two methods of estimation, ordinary least square or OLS and maximum likelihood. OLS is the most extensively used method of point estimate. Here we will stick our discussion to OLS. Ordinary least square estimation of parameters. The PRF yj is equal to beta 0 plus beta 1 xj and ui is estimated using the simple regression function y hat I, which is equal to beta hat 1 plus beta hat 2 xi plus u hat I. Plotting the regression line with y values on the vertical axis and x values on the horizontal axis, we get a trend line as shown in the figure. The SRF must be the closest approximation of the PRF since PRF is not directly observable. Our objective is to minimize the sum of squared residuals, that is sigma u hat I squared, as the estimators so obtained will carry the desired statistical properties. Sigma u hat I squared is equal to sigma bracket open yi minus y hat I bracket close squared, which is equal to sigma bracket open yi minus bracket open again beta hat 1 plus beta hat 2 into xi small bracket closed the main bracket closed squared. Sigma yi is equal to n beta hat 1 plus beta hat 2 sigma xi. Sigma xi yi is equal to beta hat 1 sigma xi plus beta hat 2 xi squared. By solving for beta hat 1 and beta hat 2 using the least square method, we get beta hat 2 is equal to n sigma xiyi minus sigma xi into sigma yi divided by n sigma xi squared minus sigma xi the whole squared, which is equal to sigma bracket open small xi minus x bar multiplied by yi minus y bar divided by sigma bracket open small x minus x bar squared, which is equal to sigma xi yi divided by sigma capital Xi squared, which is equal to ssxy divided by ssxx into sigma bracket open x minus x multiplied by 2, which is equal to ssxy divided by n minus 1, from which we get beta hat 1, which is equal to y minus beta hat 2x. Alternatively, beta hat 2 is equal to covariance xy divided by s squared x, where covariance xy is equal to sigma bracket open xi minus x multiplied by yi minus y divided by n minus 1, or else s squared x is equal to sigma xi minus x the whole square divided by n minus 1. Let us now look at how the sum of squares is calculated. The sum of squares are calculated as SSXX, which is equal to summation I varying from 1 to n bracket open x minus x bar bracket shut the whole squared, which is equal to summation I varying from 1 to n xi squared minus summation where I varies from 1 to n xi divided by n. SSXY is equal to summation I varying from 1 to n bracket open xi minus x bar into yi minus y bar, which is equal to summation I is equal to 1 to n xi yi minus xi varying from 1 to n xi multiplied by xi where I varies from 1 to n yi divided by n. SSYY is equal to summation I varying from 1 to n yi minus y bar the whole squared, which is equal to summation I varying from 1 to n yi squared minus sigma I varying from 1 to n yi the whole squared divided by n. Variance of the parameters is given by variance of beta hat 2 is equal to sigma squared divided by sigma xi squared. Variance of beta hat 1 is equal to summation xi squared sigma squared divided by n sigma xi squared. We shall now look at the sums of squares in details. Total sum of squares is equal to regression sum of squares plus error sum of squares. Total variation is the variation in the dependent variable values about its mean, which is equal to its sum of explained variation and unexplained variation. SST is equal to sigma I varying from 1 to n bracket open capital yi minus y bar the whole squared. DFT is equal to n minus 1. Total sum of squares, total variation. Regression sum of squares, explained variation due to explanatory variables. SSR is equal to summation I varying from 1 to n in bracket y I hat minus y bar the whole square, differentiation of r equal to 1. Error sum of squares, unexplained variation, which could be due to random forces, is SSE is equal to summation I varying from 1 to n y I minus y I hat squared, where the differentiation of FE is equal to n minus 2. Using the sum of squares, we get the coefficient of determination r square, which measures the percentage of total variation in the dependent variable explained by the regression model. It is a measure of goodness of fit. R squared is equal to explained variation divided by total variation, that is SSR divided by SST. That is, r square should be greater than equal to 0 and 1 should be greater or equal to r squared. From r square, we can estimate the coefficient of correlation r, which shows the degree and direction of linear association between the two variables. R is equal to sine b1 under root r squared, where r is greater than equal to minus 1 and 1 is greater than equal to r. Let us understand the method of ordinary least square with an example. Consider following data of two variables x and y, where x is the independent variable and y being the dependent variable. Estimate the regression line and the intercept and slope parameters. Solution. Consider the relationship y hat I is equal to beta hat 1 plus beta hat 2 xi plus u hat I. Using the least square method, we get sigma yi, which is equal to n b hat 1 plus b hat 2 sigma xi. Sigma xi yi is equal to beta hat 1 sigma xi plus beta hat 2 sigma xi squared. The given table calculates the value to get mean of x and y. Both are squared in column 4 and 5 and multiplied in column 3. The corresponding summations are shown in the last row. Mean of x is equal to sigma x divided by n, which is equal to 20 divided by 5, which is equal to 4. Mean of y is equal to sigma y divided by n, which is equal to 40 divided by 5, which is equal to 8. Therefore, by substituting the above calculated values in the two equations, we can write 40 is equal to 5 beta 0 plus 20 beta 1, and 230 is equal to 20 beta 1 plus 120 beta 2. Solving for beta 0, beta 1, we have beta 1 is equal to 1, beta 2 is equal to 1.75, and the regression equation is y is equal to 1 plus 1.75x. That is, a unit change in x leads to a change in y by 1.75 times. One of the important points to keep in mind is that the OLS estimators are best linear, unbiased estimators, or BLUE, BLUE, of the population parameters. Moving next to the interval estimation, instead of obtaining a single estimate of the parameters, we can estimate the parameters. We can obtain an interval of two estimates, providing a possible range of values within which the true parameter may lie. A point estimate due to problems of sampling fluctuations is likely to differ from the true value. Before coming to constructing interval estimates of beta 1 and beta 2, let us have some idea of the basic terms. Suppose we want to know how close beta 2 is to beta hat 2. We construct an interval beta hat 2 minus delta beta hat 2 plus delta, such that it contains true beta 2 with probability 1 minus alpha. Beta hat 2 minus delta beta 2 line, which is greater than equal to delta, and beta hat 2, which is greater than equal to beta 2 plus delta, is equal to 1 minus alpha, is known as confidence interval. Alpha is the level of significance. 1 minus alpha is the confidence coefficient. Beta hat 2 minus delta beta hat 2 plus delta are the confidence limits. Now we have confidence intervals for beta 1 and beta 2. Since the error term is assumed to be normally distributed, the OLS estimates of beta 1 and beta 2 are also normally distributed. Z is equal to beta hat 2 minus beta 2 divided by SC beta 2 as standard normal variate. However, since true population variance is not known, we use sigma hat instead of sigma. T is equal to beta hat 2 minus beta 2 divided by SC beta hat 2, which is equal to beta hat 2 minus B2 multiplied by summation xi squared divided by sigma hat. T follows T distribution with n minus 2 degrees of freedom. Confidence intervals for the slope coefficient beta 2 is PR square bracket open minus T alpha divided by 2. Beta hat 2 minus beta 2 greater than equal to T alpha divided by 2. This is then divided by SC beta hat 2, where T alpha 2 is greater than equal to SC beta hat 2, bracket shut, which is equal to 1 minus alpha. The PR, or probability, bracket open, beta hat 2 minus T alpha divided by 2 SE beta hat 2, which is less than beta 2, which is less than beta hat 2, plus T alpha divided by 2 SC beta hat 2, bracket shut, which is equal to 1 minus alpha. And 100% 1 minus alpha confidence interval for beta 2 is beta hat 2 plus minus T alpha divided by 2 SE beta hat 2. Similarly, the confidence interval for intercept coefficient beta 1 is given by probability bracket open beta hat 1 minus T alpha divided by 2 SE beta hat 1, which is less than beta 1, which is less than beta hat 1, plus T alpha divided by 2 SE beta hat 1 bracket shut equal to 1 minus alpha, or 100% in bracket 1 minus alpha percent confidence interval for beta 1 is to beta hat 1 plus minus T alpha divided by 2 SE beta hat 1. We can see that the size of the confidence interval is proportional to the standard error of the estimate. Greater the standard error, bigger is the confidence interval, and greater the uncertainty associated with estimation of true population parameters. Now let us look at the confidence interval for sigma squared. The statistics x squared is equal to n minus 2 multiplied by sigma hat squared divided by sigma square follows chi-square distribution with n minus 2 degrees of freedom. The confidence interval for sigma squared is PR bracket open x squared 1 minus alpha divided by 2, which is less than x squared, which is less than x squared 1 plus alpha divided by 2, the whole thing equal to 1 minus alpha. PR bracket open n minus 2 bracket shut sigma hat squared divided by x squared alpha divided by 2, which is less than sigma squared, which is less than n minus 2 into sigma hat squared divided by x squared 1 minus alpha divided by 2. The whole thing should be equal to 1 minus alpha. Moving further, we shall now discuss hypothesis testing. The concept of hypothesis testing is used in decision making. For example, a manager would want to know if he can raise the price of his product or not. A hypothesis is a proposition that we want to verify whether it is true or not. Since the data are of different types and cannot be analyzed in a uniform way, we use appropriate statistical tools and techniques to analyze the data. There are two approaches for hypothesis testing: confidence interval and test of significance. There are different statistical tests for hypothesis testing. The choice of test depends upon the nature of the problem under study, the power of the test, the sampling method, etc. First, we shall understand the confidence interval approach. For the purpose, construct a 100, that is 1 minus alpha percent confidence interval for the estimate. If the estimate comes under the confidence interval, accept the null hypothesis. Finding is statistically insignificant. And if it falls outside the interval, one should reject the null hypothesis. Test of significance approach. Under the test of significance approach, the sample results, for example, the test statistical estimator, are used to reject or used to reject or accept the null hypothesis. A value of the parameter is hypothesized and we check whether the computed value lies within the confidence limits around the hypothesized value. Moving further to understand the t-test, the test is generally used to check whether the slope parameter is equal to the hypothesized value or not. Suppose true beta 2 is specified in a null hypothesis. Now we know that statistic t is equal to beta hat 2 minus beta 2 divided by SC beta hat 2 follows t distributions with n minus 2 degrees of freedom. The confidence interval is beta 2 is PR bracket open beta 2 minus T alpha divided by 2 SE in brackets beta hat 2, which is less than beta hat 2, which is less than beta 2 plus T alpha divided by 2 SE beta 2 bracket shut, which is equal to 1 minus alpha. The limits of the confidence interval specify the region of acceptance of the null hypothesis. If the computed value falls outside the interval known as the critical region, then we reject the null hypothesis. We shall now understand t-test graphically. The diagram shows a student's t-distribution with 30 degrees of freedom. For a two-tailed test with a significance level of 0.05, the critical values are 2.042 and minus 2.042, and the critical region is the area marked to the left and the right of these critical values. The combined area or the shaded portion of the critical region is 0.05. The area of the region of acceptance is 0.95. Suppose the computed t value is 4.93 and the null hypothesis is h of 0 to beta 2, which is equal to 2. We observe that the t statistic falls in the area outside the region of acceptance, that is in the critical region, and therefore leads to rejection of the null hypothesis. By contrast, any value of t statistic below 2.042 will lie in the acceptance region and therefore shall lead to acceptance of null hypothesis. Next, we have one-tailed t-test. The testing procedure is similar as in the two-tailed test, except we consider one side of the tail and check if the computed t value lies within or outside the critical region. Let us understand t-test with the help of an example. Consider a Cobb-Douglas production function. Q is equal to A, K raised to the power of alpha, L raised to the power of beta, E raised to the power of mu. It is estimated as log Q is equal to 1.37 plus 0.632 log K plus 0.452 log L. SC alpha is equal to 0.257, SC beta is 0.219, R2 is equal to 0.98, covariance alpha beta is minus 0.055. You are required to test the hypothesis that alpha and beta are identical. Solution. Null hypothesis H of 0 is to alpha is equal to beta. H1 alpha is not equal to beta. Under the H of 0 we have alpha minus beta equal to 0. SC alpha minus beta is equal to variance of alpha plus variance of beta minus 2 covariance alpha beta, which is equal to 0.062. The t statistic is bracket open 0.632 minus 0.452 minus 0 divided by 0.062, which is equal to 2.90. At 5% level of significance, since the t statistic 2.90 is greater than 2, we say that the results are significant, and hence we reject the null hypothesis that the two coefficients are identical. Next, we shall look at the x squared test significance testing of sigma squared. As stated previously, the statistic x squared is equal to n minus 2 multiplied by sigma hat squared divided by sigma square following chi-square distribution with n minus 2 degrees of freedom. Null and alternative hypothesis. One side upper tail. H0 is sigma squared, which is less than sigma 0 squared, and HA is sigma squared, which is greater than sigma 0 squared. One side lower tail. H0 is sigma squared greater than sigma O squared, while HA is sigma squared less than sigma 0 squared. Two-sided. H0 sigma squared, which is equal to sigma 0 squared, and HA is sigma squared not equal to sigma 0 squared. Understanding the significance of sigma squared with the help of an example, suppose we want to test the hypothesis that population variance is equal to a specified value, say sigma squared is equal to 80, and we've computed sigma hat squared is equal to 40.15. Degrees of freedom is 8. Now we want to test the hypothesis under 5% level of confidence. Here H1 is sigma squared not equal to 80 and computed x squared is equal to 3.0105. The critical x squared value are 2.179 and 17.53. Since the computed x square lies within these two limits, we accept the null hypothesis. Moving further to the decision rules based on the chi-square distribution with degrees of freedom equal to n minus 2. One side upper tail reject h0 if x computed squared is greater than xu squared, which is equal to xa squared. One-sided lower tail reject h0 if x computed squared is less than xl squared, which is equal to x1 minus a squared. two-sided. Reject h0 if x computed squared is less than x cell squared, which is equal to x1 minus a by 2 squared. Conclude that sigma o squared is greater than sigma squared. Now look at the ANOVA F test. The F test is used to test the overall fit of the regression model. It is based on the analysis of the sum of the squares. As stated earlier, the total sum of squares is equal to regression sum of squares plus error sum of squares. Total variation is the variation in the dependent variable values about its mean, which is equal to the sum of explained variation and unexplained variation. So we have SST is equal to sigma I from 1 to n in bracket yi minus y bar the whole squared. DFT is equal to n minus 1. Total sum of squares, total variation. Regression sum of squares is explained variation due to explanatory variables. SSR is sigma I is equal to 1 raised to the power of n in brackets yi hat minus y bar the whole square. DFR is equal to 1. Error sum of squares is unexplained variation due to random forces. SSC is equal to sigma I from 1 to n yi minus yi hat the whole square. DFE is equal to n minus 2. F is equal to ms of SSR divided by ms of SSE, that is beta 2 hat squared into summation xi squared divided by sigma hat squared. The ANOVA table is constructed as shown in the table. The table gives information on source, degrees of freedom, the type of sum of squares, mean square, and the F value. The test of hypothesis H0 equals beta 2 equals 0. F variable is equal to beta 2 squared multiplied by sigma xi squared divided by sigma square follows F distribution 1 degrees of freedom in numerator and n minus 2 degrees of freedom in the denominator. To test the hypothesis that true slope parameter beta 2 is 0, compute the F statistic and compare it with the critical F value at the chosen level of significance. If the F statistic is found to be insignificant, then accept the null hypothesis, and we can say that independent variable has no linear influence on the dependent variable and variations in it are entirely explained by the error term. Let us now understand the problem of prediction. The regression line can be used to predict or estimate an observation. For example, a consumption function can be used to predict future consumption expenditure corresponding to some level of income. There are two kinds of prediction: mean prediction, interval prediction. First, let us look at the mean prediction. It refers to estimation of condition mean of dependent variable at the chosen level of the independent variable, say xi, that is a point on the regression line. The point predictor is best linear unbiased estimator. xp, the particular or given value of the independent variable x. Yp, the value of the dependent variable y corresponding to the given xp. EYP is the mean or expected value of the dependent variable y corresponding to given XP. YP hat is equal to B0 plus B1 XP, the point estimate of EYP when X is equal to XP. Since our objective is to know how close y hat p is to true mean value of y, we have to make an inference about the sampling distribution of y hat p. For the purpose, we have to estimate the variance of y hat p. It is computed as s square y hat p equal to s square bracket open 1 divided by n plus xp minus x bar the whole square divided by sigma x 1 minus x bar the whole square bracket shut. The 1 minus alpha 100% confidence interval for EYP is given by y hat p plus minus t alpha by 2 SYP. Next, we should look at the case of individual prediction. It refers to prediction on individual value of dependent variable y for a given value of dependent variable x, say xi. Considering a regression equation, yi is equal to beta 0 plus beta 1 x1 plus ei. Suppose we want to predict a future outcome when x is equal to xi. The point estimate of mean production will be yi is equal to b0 plus b1 xi. The 1 minus alpha 100% prediction interval for yi is equal to beta 0 plus beta 1 x1 plus ei. yi hat plus minus t alpha by 2 n minus 2 syx under root 1 plus h1. hi is equal to 1 by n plus xi minus x bar the whole square divided by summation I moving from 1 to n bracket open xi minus x bar the whole square, where syx is variance of y values about mean y and hi is the variance of the estimator y hat I. Let us now summarize what we have learnt in this module. Regression analysis involves prediction of average value of dependent variable on the basis of fixed values of the independent variable. The concept of statistical inference has two branches, estimation and hypothesis testing. The theory of estimation consists of two methods, point estimation and interval estimation. The point estimate of a regression coefficient is estimated using the method of ordinary least square using the sample regression function. Under confidence interval approach, we obtain an interval of two estimates providing a possible range of values within which the true parameter may lie with specified probability. Under the test of significance approach, the sampled results, that is the test statistic estimator, are used to reject or accept the null hypothesis. A value of the parameter is hypothesized and we check whether the computed value lies within the confidence limits around the hypothesized value. The test statistic follows probability distribution such as normal, t, chi-square or f. Mean prediction refers to estimation of condition mean of dependent variable at the chosen level of the independent variable, say xi, that is a point on the regression line. Individual prediction refers to prediction on individual value of dependent variable y for a given value of dependent variable x, say xi.